In this webcast, we want to interpret the molecular orbital diagram of carbon monoxide. We'd like to make a connection between the Lewis structure, which is shown here, oxygen on the left, carbon on the right, and the molecular orbital diagram over here, again, oxygen on the left, carbon on the right. We're going to begin the process by adding electrons to this molecular orbital diagram. We know that there are 6 valence electrons that come from oxygen. There are 4 valence electrons that come from carbon. Those 10 valence electrons altogether needed to be added from the bottom up, the bottommost molecular orbital up, until we've exhausted all 10 electrons. On the left-hand side of this diagram, we have orbital pictures that correspond to each of these different molecular orbital energy levels. Psi 1, for example, is our sigma S level. Psi 2 corresponds to that next level up, sigma SP. Then we have our pi, and we have our pi star levels there for 3, 4, and 6, and 7. Psi 5 corresponds to what's labeled as sigma SP star, and Psi 8 corresponds to sigma P star. Let's look at these pictures and try to make some idea how they relate to the Lewis structure. Now, this connection between the Lewis structure and the MO diagram is not perfect, but I do believe that there's value in trying to make this connection where you can see the relationship between our models that we're familiar with and the new model that we're trying to get some intuitive understanding of. Let's start by looking at this level here. The picture of that MO is shown over here, and mostly what you see in this picture is the orbital surrounding that atom on the left, the oxygen atom. It's essentially a picture of an atomic orbital that's oxygen-centered with very little contribution from carbon. This lone pair is probably best represented by Psi 1, the molecular orbital that's predominantly an atomic orbital centered on oxygen. We can continue this process and look at Psi 2, and if we compare Psi 2 to the molecular orbitals that we drew on sheet 1, well, Psi 2 looks almost exactly like a sigma SP molecular orbital. You can see that there's a change in sign of the wave function of this MO at the oxygen. That means oxygen contributed its 2px orbital, and combined with the 2s orbital on oxygen, which is the larger of those 2 lobes. And there's only one node, and that node occurs exactly centered on the oxygen atom. So Psi 2 looks like it is a bonding contribution. From sheet 1, it looks like a bonding SP contribution. In our Lewis structure, the sigma bond between the oxygen atom and the carbon atom corresponds to Psi 2. The pi levels are interpreted as pi orbitals that are along the z-axis and along the y-axis. Sigma SP star looks like sigma SP star from sheet 1. In other words, it's an anti-bonding contribution. You can see there's a node not on one of the atoms, but it's in between the 2 atoms, which indicates that it's an anti-bonding orbital. This portion off to the left that's centered on oxygen, what's inside that box looks like a p orbital that has interfered destructively with an s orbital that came from carbon. That looks like sigma SP star from sheet 1. And if we look at the size of the lobes, the size of the lobe gives an indication of which atom contributed most to that molecular orbital. And we can see from the diagram that the lobe that's on carbon seems to be quite a bit larger than the lobes that are centered around oxygen. A very likely conclusion is that the lone pair that's on carbon in our Lewis structure is best represented by Psi 5, that anti-bonding contribution. Overall, we have a bond order of 3. There's one sigma bond that we concluded in our interpretation was that sigma SP bond, and there are 2 pi bonds, and then there are lone pairs that I've checked corresponding to sigma S and sigma SP star.